All right, even though we've been focusing on uniformly accelerated motion, we know not all motions have uniform acceleration. So here we can take a look at a couple of interesting examples when the acceleration is not quite uniform. The first example is from the textbook. So you see this picture, there's a Boy Scout who is pulling on a package suspended from a tree. So he walks at a constant speed, v0, away from the tree, holding a rope. And as he pulls the rope away from the tree, the package goes up with a speed v. Now, even though he moves away with a constant speed v0, the speed at which the package goes up the tree is not uniform. V is not uniform. And even moreover, even the acceleration of the package going up is not uniform. We can see from the calculation. Now, strictly speaking, this is a two-dimensional problem, but we can think of it as two related one-dimensional problems. One is the motion of the Boy Scout horizontally. The other is the motion of the package going up vertically. Each is a one-dimensional motion, and they are interconnected. Now, here's the thing you have to be careful about. As the Boy Scout walks forward horizontally at a speed v0, the speed of the package going up is not the same as v0. It's because the reason why the package goes up is because he is pulling on the string, so he is lengthening the part which is labeled L. Okay, so L increases, right? Does L increase uniformly? Not quite. You see, it's not quite the case. X does increase uniformly. Okay, X is the distance, horizontal distance measured from the package. That does increase uniformly, but L does not. And the thing is, when L increases, the package will go up because the entire length of the rope is fixed. That is very important in our analysis. Let's say the entire length of the package of the rope is, say, 4 meters. All right, and out of that, L is equal to 3 meters, and the vertical part of the rope is 1 meter at some point. Right? We can do a little labeling here. So we label this part. We call it 1 meter at this moment, and the length of the cable, the other part of the length, this part at that moment, is 3 meters. Right? The sum is 4 meters, which will not change. Let's say the next moment, L increases to 3.1 meters. That means the yellow part, the vertical part of the rope must be shortened by 0.1 meter, right? So as L increases by 0.1 meter, the package goes up by 0.1 meters. That tells me that the rate at which the package goes up is the same as the rate of L increasing. So V is actually equal to the L dt. That's something to keep in mind. V is the speed of the package going up. The L dt is the rate at which L increases. Now, how does one relate L with X? We look at this right angle triangle here. Okay? You look at this right angle triangle here. If you include this part and this part, L is the hypotenuse, and the base is X. The other vertical side has a fixed length of H. You can see that, right? It's H. So we have L squared equals H squared plus X squared. L and X both change, but H does not. Right? That's the Pythagorean theorem. Now I'm interested in the L dt, which is V. How is that related to V0? We know V0 is actually the rate at which X increases. So V0 is dx dt, which is fixed. Right? So how do we get dl over dt and find its connection with dx over dt? See, all we have to do is take a derivative of this equation. Every term I take a derivative with respect to time, and I can get my answer. So that's what I'm going to do now. I'm going to take a derivative. Okay, so you take d dt of L squared must equal to d dt of h squared plus d dt of x squared, right? I'm just taking derivative with respect to time for every term. The first term is just 2L dl dt. The next term, d dt of h squared, but h is constant, right? H is constant, so that's 0. The next term is d dt of x squared, that's 2x dx dt. But wait, dl dt is just v, that's the v we're looking for, and dx dt is just v naught, which is the fixed speed of the Boy Scout moving away from the base of the tree. So I can rewrite this as lv equals to x v naught. Therefore, I find v to be equal to x over L times v naught. Okay? Now you can obviously see here, even though v naught is a constant, v is not a constant because x increases and L also increases. And but x over L varies because actually x over L, you can see here, is cosine of this angle theta here. Theta changes. So therefore, v is not uniform. Okay, as a matter of fact, you can look at the special case when x equals 0. When x is equal to 0, the Boy Scout is right underneath the package. So the Boy Scout is right here when x equals 0. And so he walks horizontally away. By doing so, does he really change the length L at this moment? No, because he's not pulling along the direction of L. Rather, he's, L at this point, this segment of string is vertical, but he's moving horizontally, right? So he is not pulling on the rope along this direction. Therefore, he's not changing L at this point, and therefore v is also equal to 0 because v is dl over dt. So when x equals 0, v is also equal to 0, which makes sense. On the other hand, as he walks further down, theta becomes smaller and smaller and smaller. When theta is very close to 0, the string, the L part of the string, this hypotenuse is virtually horizontal. So that is essentially the same direction as his direction of motion. So, as he walks, say, forward by a distance of 1 meter, L is going to lengthen by essentially 1 meter. Therefore, the package is going to go up essentially by 1 meter. So when L is quite long and theta is quite small, we say that v and v naught become roughly equal to each other. And that's exactly what you can see here. When x and L are almost equal to each other, I mean, x is always less than L. But when x and L are almost equal to each other, meaning theta is very small, then v is almost equal to v naught. Okay, so it makes perfect sense. So that is an interesting case of two related one-dimensional motion with non-uniform speed, and you can even calculate the acceleration, and you find it's even the acceleration is not uniform because after all, a, let me change the color here, a is equal to dx over dt. I mean dv over dt, right? So we write a as dv over dt. Let me change the color now. Let me use a different color. But v itself is x over L v naught. So that's d dt of x v naught over L. Now we know v naught is a constant, so I can take that out. It's v naught times d dt of x over L. Now x and L, they both change as a function of time. So you're looking at d dt of a ratio or fraction, right? Is dt of, say, f over g. You know how to do that, right? So you apply the formula you learned in your math class for calculus. So it's equal to v naught times, you first square the denominator, which is L squared, and then you go dx over dt times L, then minus x times dl dt. That's the formula we learned from calculus, right? And you notice that dx dt is v naught, dl dt is v. So you can simplify this, and it turns to be equal to v naught squared over L. V naught squared over L minus x v naught over L squared times v. So clearly, it is not a constant. It is not a constant. Okay, because as time goes by, L changes, X changes, and V changes. So you don't get a constant. Interestingly enough, when X equals 0, you don't have the second term here, and the answer is A equal to V naught squared over L. This, in fact, can be explained as we move on to chapter 4, two-dimensional motion, especially circular motion. Okay, we're getting ahead of us. But when you go to chapter 4 to study circular motion, you will find that it actually makes sense for the acceleration to be equal to V naught squared over L when X equals 0. So when the Boy Scout is right underneath the package. So he is moving perpendicularly away from the rope he's holding on to. And then you will find why the acceleration equals his speed squared divided by L. You will see that at that time. Okay, so this is one example. Now let's look at a second example. The second example has to do with what's called terminal velocity. What's terminal velocity? Well, you consider something falling from the sky. Okay, so I have a picture of the skydiver, of skydivers in this case. You have a picture of the skydivers. They start going down from a very high position. Okay, and they have an acceleration A. What is A equal to? Well, in a true free fall, A equals G. Okay, A equals G. But it's not a true free fall because in the real world, you always have air resistance. Okay? I'm not even talking about opening the parachute. I'm just saying, just by themselves. If they don't change anything, they don't open up the parachute, their acceleration cannot be equal to G all the time. Because as they go faster and faster due to gravity, they're going to encounter greater and greater air resistance. I mean, it's common sense that as you go faster through the air, you encounter more air resistance. So that amounts to a reduction in the acceleration. And that reduction has to do with your speed. Okay, the greater your speed, the greater the reduction. And as a reasonable approximation, we can often write this as a constant B times the speed itself, V times V. Okay, so the reduction due to the air resistance increases as the speed increases. Okay, this makes it a non-uniformly accelerated motion. And we can see this is absolutely necessary. Without this additional term, we'll be in big trouble. We're not talking about skydivers, crashing down on your roof or something. We're talking about something far more common, that is raindrops. Consider a drop of rain falling from the cloud all the way to the ground. Let's say the height from which the raindrop starts before getting to the ground is h. Okay, h. And let's pretend the acceleration is g. It doesn't change. You ignore any resistance from the air. And then we have uniformly accelerated motion. It starts out at 0 speed. Okay, then it goes down after falling down distance h vertically. It's going to crash to the ground at a certain speed. I want to know what that speed is. And the result is just astonishing. The result is astonishing. So you start from here. You end up there. What's the final speed equal to? Well, the distance is h. Okay, the distance is h. So that's h. The initial speed is 0 in this case, or close to 0. I want to know what the final speed is. The acceleration A equals G, which I put a question mark on. But let's suppose that's the case. V naught, H, A, you want to find V. There is no T, there is no time involved. What's the best formula to use? Well, there's a formula, one of these 4 formulas without T in it, and it's V final squared minus V initial squared equal to what? 2A delta X. And A is G in this case, and delta X is H in this case. Okay, so cross out V initial because that's very close to 0. We can assume that safely. So V equal to square root of 2GH. Okay, that's how fast the raindrop will be falling after going down distance h in a free fall. And let's look at some reasonable numbers. Let's say h is a mile. Okay, 1,609 meters. So let's find the final speed. Okay, 2g is 9.8 meters per second squared. H is 1609 meters. That's a mile. And if you do the algebra, you'll find the speed to be 178 meters per second. Wow, that's a lot. The fastest human can run at roughly 10 meters per second. This is 17.8 times as much. Very fast. And if that doesn't ring the bell, you can convert that to miles per hour. I mean, just use 1 mile equal to 1,609 meters, and 1 hour equal to 3,600 seconds. And if you do so, you will find the answer in miles per hour. It's 396 miles per hour. Oh my God, look at this. This is crazy. Imagine this drop of water crashing on your head at nearly 400 miles per hour. What do you think is going to happen to your head? It's going to explode, or it's going to form holes on it, right? So we cannot survive if that's the case. On a rainy day, our roof will collapse, and if we go out, we're going to die. In reality, that doesn't happen. Why? Because as the water falls down, it encounters air resistance. So the acceleration is not g, rather it's g minus a term due to its speed. And if we assume it's proportional to speed, then we go back to here. We go back to here, and we can now imagine how the speed changes as a function of time with air resistance, okay? With air resistance. So this is v, this is t. Now, without air resistance, it's going to be a straight line because the speed wouldn't change, right? The speed wouldn't, the acceleration wouldn't change. The slope is a constant. The slope equals g. Okay, so here's the hypothetical case when there is no air resistance. But with air resistance, there is still an acceleration which is still downwards, which means you're still going faster and faster, but the acceleration is not a constant. Let's see how the acceleration changes over time. Initially, when you start from rest, this term is very small because v is almost 0, right? So a is essentially equal to g, which means initially you're going to start out at a acceleration which is almost the same as g. So you're going to start out like this. You're going to start out like this, okay? But gradually, as you go faster and faster, this next term, negative bv, starts to get more and more important. So the acceleration becomes less, even though it's still positive, which means you're still going down faster and faster. So the slope, which is the acceleration, will start to decrease. So it's going to deviate away from the straight line. It's going to go like this. Get fatter and flatter and flatter. Now, at some point, you're going so fast that g minus bv equals 0, because v is so large, it satisfies g minus b equal to 0. What is the acceleration now? 0, which means what? You can no longer accelerate because the acceleration is now 0. Okay, then we say you have reached what? Terminal velocity. So it becomes totally flat, okay? And if I were to draw a line parallel to the t-axis, I'm going to get this. That is called terminal velocity, vt. Okay, so the red curve is a more realistic rendition of what really happens to the speed as an object falls from a high elevation. You have to consider air friction because typically that produces large speed due to the acceleration of gravity, which then in turn causes a lot of air resistance. Okay, this is the reason why the actual speed of water drop, the terminal velocity, is much, much less. I don't remember the exact figure, but something like 10 meters per second, which we can easily tolerate. It's actually not bad at all, instead of 400 miles per hour, which is crazy. Okay, and so that's terminal velocity. And how do you find terminal velocity, by the way? Terminal velocity happens when the acceleration is 0, so the velocity can no longer be increased, so that's why it's terminal velocity. And so set a equal to 0, which gives us g minus bv equal to 0. That is the terminal velocity. So vt equals to what? G over b. Okay, so we know what the terminal velocity is. It depends on the acceleration of gravity, but also depends crucially on this factor, on this parameter b. Okay, b depends in turn the shape and size of the object sailing through the air. If you open up a parachute, you are going to increase b. Okay, you just make the cross-section area much bigger, therefore you encounter more air resistance. So the acceleration becomes even less. So reason why a parachute can really stop you from, from reaching a very high terminal velocity is because it increased the b value effectively, therefore decreasing the terminal velocity. Okay, now, given this acceleration, even though it's not uniform, we know the expression at least. Can we find v as a function of time? That is, can we find the exact shape of this red curve? Well, let's do that, okay? Let's try that. A is dv dt, right? So we know dv dt equals to what? G minus bv, right? So that's the equation we have for v. Okay, it's not uniform, but we can still find what v looks like as a function of time. We can still solve for it. So question is, how do you do that? Well, there are a couple of things we can do. Okay, one is you can just, find the solution mathematically. Find a solution mathematically, and it's not that hard to do, even though this is technically a differential equation, because you're looking for a solution which is an unknown function being differentiated. It's not an algebraic solution whose answer is just a number or a bunch of numbers. You can still solve this quite easily because t only happens here. Okay, t only shows up here. So what you can do is you can move everything to the other side, leaving only dt on one side. So you can solve for dt basically. You solve for dt. So dt equals what? You move dt to the other side and move this g minus bv down to this side to combine with dv. dv over g minus bv. This is called a separation of variable. It's a very crucial technique in solving differential equations. This course does not need any differential equations, but you're seeing the first one actually, and it's quite easy to solve because we have successfully separated the variable t on one side and v on the other side. After this, we can integrate. Okay, we can just go ahead and integrate between the two over both sides of the equation, and let's see what we come up with if we did that. We integrate and we integrate. Okay, we have to give it the upper and lower limits. So let's say we start the timer here, t equal to 0, and end up at the current time t. In the meantime, the speed of this object, initial speed when t equals to 0, we call it 0. It doesn't have to be, but it just make it easier. The current speed is v. Okay, I want to know v as a function of time. So how do we get that? We just integrate over both sides. Okay, the left hand side is just t. When you integrate, it's just t. Okay, the right hand side is you have to take more effort. T equals what? How do you integrate the right hand side? Well, I trust that you know how to do that, but I can give you a quick overview of how a review of how to do that. You can define a variable u as g minus bv. Okay, then if you did that, that's just u, right? It's just u, and dv on the other hand is related to du. du equals to, if you differentiate that, negative b dv. So dv equals negative b over du. So I can write the du here with a negative b, negative 1 over b here, right? Because after all, dv equals du over negative b. So that's what I did here. The upper and lower limits also change. The lower limit is 0 for v, but for u it is g minus b times 0, so it's just g, right? The upper limit is v for v, but for u is g minus bv. So g minus bv. All right, so we can easily integrate the right hand side now. It's just a natural log of u. The natural log of u going from g to g minus bv. And we all know how to do that. That's negative 1 over b, natural log of upper limit over lower limit. So it's g minus bv over g. Okay, that is what t equals to. But I don't want to know what t equals to. I want to know what v equals to as a function of time. So what I'm going to do now is I'm going to rewrite this as a natural log function. So the natural log function of 1 minus bv over g equals to moving negative 1 over b to the side negative bt. Right? And how do I get rid of the natural log function? Easy. I'm going to raise both sides to the power of e. Raise both sides to the power of e. And we know e to the natural log of x equals x itself. So therefore, this is just 1 minus bv over g. Okay, so we can now easily solve for v. So v as a function of time, I know what it is equal to now. It is equal to g over b, and then 1 minus e to the negative bt. Okay, so we found v as a function of time. It's like this. This is the mathematical expression of this red curve that you see here. This red curve that you see here. Let's see if it makes sense. Okay, at t equal to t very close to 0. Okay, so let's look at a special case where t close to 0. So you're just beginning to fall. Then e to the negative bt. That's very negative bt is very close to 0, so it's roughly equal to 1 minus bt. You know how to do the approximation, and therefore 1 minus this, 1 minus this. So 1 minus e to the negative bt is roughly equal to bt, right? And therefore, v of t is roughly equal to what? G over b times bt, so gt, right? That makes total sense because when t is very short, v is very small, so there is very little air resistance, which is proportional to v, and therefore the acceleration is essentially g, and therefore the speed is roughly gt, okay? But that starts to change when time progresses, when v becomes so large that you cannot ignore air resistance anymore. As a matter of fact, when t goes to infinity, so at t approaching infinity, what happens to the equation? Well, e to the power negative bt would approach what? 0, right? Because essentially e to the power negative infinity, which is approaches 0. So then v of t approaches what? G over b, and then 1 minus 0. And that's just the over b. That's exactly what we get for terminal velocity. Look at terminal velocity that we got. Where did we get terminal velocity? Terminal velocity right here. Right here, g over b. But here we took so much effort, we found this, we established the equation, we solved, and look at the special case mathematically by taking the limit of t approaching infinity. The answer is g over b. But here it's much easier because we simply realize that the terminal velocity takes place when there's no longer any acceleration. Just set the acceleration equal to 0. That's all. Okay, so it works. And so here is an important example of non-uniformly accelerated motion. And once again, we owe our safety and existence to the fact that there is air resistance for a high-speed object going through the air. Otherwise, we wouldn't be able to survive, crashes of whatever even small objects from the sky. Okay, now there is another way to work out this solution here without going through this integration, and that is by guessing what the answer is. Okay, by guessing what the answer is. And I'm not going to talk about it here, but you will see equations similar to this on many different occasions, different parts of physics. For example, in electricity and magnetism, you're going to see equations like that for charging and discharging of the electrical capacitor. Very similar mathematical expression with very similar curves. And over there, we will see how to solve this equation more intuitively without even using this formal technical method of integration by guessing what the answer is. All right, but for now, if you can solve this equation, you can solve this like this, you'll be fine. So these are the two examples that we discussed for non-uniformly accelerated motion. But again, we're going to focus primarily on one-dimensional motion with uniform acceleration. And that is the end of the lecture for chapter 2.